And Newton's theory was so successful, it had amazing predictions that were confirmed over and over again for 200 years. One of the most important ones for us is that of the motion of the planet Neptune. So you see here depicted a little ball. This is my, well, an artist's rendition of Neptune moving around the sun. This is not to scale, okay? And when people observed the motion of Neptune, they saw that it didn't move exactly as predicted by the theory of Newton. There was an anomaly, okay? And so people said, well, clearly Newton's theory is correct. What must be going on is that there must be another planet farther away from Neptune, okay? A planet over here that we have not detected yet. So if we just point all our telescopes where that planet should be, we should be able to find it because Newton's theory is correct. And indeed, they pointed the telescopes there, and they found Uranus, which is the last planet. Well, let's leave that for a different day. Right, and so Newton's theory succeeded once more, and people were super happy. So naturally, when people observed the motion of the planet Mercury, and they saw that it moved in an ellipse. It had some eccentricity around the sun, but it didn't quite move as Newton predicted. They said, aha, I know what's going on. There must be another planet we have not seen, right? Okay, it worked for Neptune. Why wouldn't it work for Mercury? So they said, okay, let's call that planet Vulcan, like the Vulcan from like Star Trek, which has also related to like a Roman god of fire, doesn't really matter. But that planet had to be very close to the sun, according to calculations, using Newton's theory to explain the motion of Mercury. And, you know, when they pointed their telescopes over there, they couldn't find this planet Vulcan at all. As a side story for the students, when you're trying to like detect a planet very close to the sun, you should always avoid pointing your telescopes at the sun. I'm saying this based on personal experience because that will completely destroy your telescope. Like it'll burn, it's bad. Okay, so enter Einstein, right? So it couldn't be a planet. What was going on? So according to Einstein, Newton's theory was just completely wrong. We had to completely revise our understanding of gravity and actually of all of physics. It was a quite radical point of view. So the cornerstone of his theory is that space and time form a continuum, which I'm depicting here with lines, okay? And you know, this continuum, we're going to call the continuum space-time because we're very creative. Now, space-time can stretch and it can curve due to the presence of dense objects like stars, like the sun. And when that happens, according to Einstein, gravity becomes a manifestation of the curvature of space and time through some complicated mathematics that he wrote down. So what you're seeing here is an animation of how these rods, so you can imagine essentially rods connecting every vertex here and how they stretch when you put in the sun in the middle of the box. You should also be picturing that at each intersection here, there's a clock. And clocks also happen to slow down, according to Einstein, when you are close to a gravitating body. And it's that stretching and dilation of time that we perceive as gravity, okay? So that sounds insane. How does that explain the motion of planets? You know, you're stretching space-time, why does that matter? Well, think of it this way. If Earth is curving space-time, and this is a slice of that box that I showed you earlier, then the moon will just try to follow a straight path in this curved geometry. But it can't, because the geometry is curved, right? And so every time it tries to go straight, it gets banked by the curvature of space-time. So from the point of view of the moon's following a straight path. But from the point of view of us, standing outside of the Earth and the moon, we see the moon going in a circle. Okay? It's about reference frames in that sense. Yes? We'll get to that in a second. So just like Earth bends the geometry of space-time, of course, the sun, in principle, should bend the geometry of space-time. And anything that is in this curved geometry will then follow a curved path, okay? From our point of view, a straight path from their point of view, okay? So the types of orbits that you can have in the solar system are not perfect circles, right? So in Newtonian gravity, you can have a circle, okay, for the orbit of a planet around the star. You can have an ellipse, which is like a stretched circle, okay? Or you can have orbits that are not bound, meaning you can shoot a satellite to go really close to the sun, slingshot, and then head out, right? That's called an open orbit, okay? In Einsteinian gravity, the circle can still exist, but the ellipses don't quite close in the same way. So they form these petals, okay? Just like the petals of a flower. That's called precession of the elliptical orbit, and that explains Mercury's motion, okay? So because gravity is not a force, it's a curvature of space-time, Einstein's equations lead to corrections to Newtonian gravity, and those corrections make the motion of Mercury not be as Newton predicted. The motion of Mercury is going to be different, and that difference happens to match exactly with the experiment, or with the observations that they had observed. It's fantastic. And I want to pause here because you're going to say, oh, well, of course, they had already observed the motion of Mercury, so anybody can come and construct some theory of gravity, some mathematics that will produce motion of Mercury that matches that observation. But that's not quite how science works. What makes science special, what makes physics special, is that it doesn't matter who you are. It doesn't matter if you're a man, if you're a woman, if you're black, if you're white, if you speak English, or if you speak Spanish or a different language, what your religion is, how smart you are, how pretty your mathematics are. If your theory doesn't match experiment, it's wrong. Period. Okay? And if your theory doesn't predict anything we can measure, then it's not physics. Period. Okay? And I can repeat the experiment here and in Asia and in Europe, and I will get the same answer. Period. Okay? And I can do it today, and I can do it tomorrow, and I can do it yesterday, and I'll still continue to get the same answer. The experiments are repeatable, okay? And the predictions are unique. So far, Einstein could be totally wrong, because he hasn't really made a prediction that you can go and then look at, search for, and confirm, or, destroy his theory. He's made a post-diction, okay? So what else does Einstein's theory predict? So this is back still in the early 1900s. He said, well, if everything follows a curved path, when the geometry of space-time is curved, then light surely also follows a curved path. Like, why not? Light is not special in that sense. Has energy. So if you have a star, switch hands, over here, and it's emitting light, it's very far away from Earth, and there's nothing between the star and Earth. Let's pretend there's nothing between the star and Earth. Then the star's light will just follow a straight line, hit straight Earth. Great, no problem. But what happens if you put something in between? If you put the sun in between, then obviously this light that goes straight through is never going to get to you because it's just going to hit the sun, right? So what happens if this geometry of space-time is curved is that the light emitted by the star, the light is emitted in all directions, right? So there's some rays that are going to go in this direction. Because of the curvature of space-time, that light's going to bend, and then you're eventually going to see that light at Earth. But if you don't know that light curves, then you are going to think that the light that you detected didn't come from this spot, but came from a straight line over here. So if you don't think space-time is curved, the star is here. If you think the space-time is curved, the star is here. So how do you figure out where the star is. It's not like I can send Jan or a grad student to the star to tell me where the star is. So I do what's sometimes called a differential measurement. I measure the location of the star when the sun is between Earth and the star, and when the sun is not between Earth and the sun 6 months later, because fortunately, we move around the sun. Okay? And that's exactly what Sir Arthur Eddington did. So you see, if space-time is really curved, the light should follow a curved path, as I showed before, as it travels from the stars to Earth. Now, if the sun is between Earth and the stars, then the star's light would have to bend around the sun before it reaches us. So that's a bunch of stars emitting light and the light getting bent in that sort of ring. It's almost like you have a lens. So Einstein made a prediction that this would happen. Not only did he make a prediction, he said like, oh, something like this should happen. He actually predicted exactly how much the star should move as perceived by Earth, okay? And this effect was not only observed, it was measured, and it was found to match the measurement exactly what Einstein had predicted. And that's a calculation that Einstein himself did in 1915. And that's the story of Arthur Eddington. During a solar eclipse, Eddington photographed stars that are very close to the sun. And those are here. They should appear some. There we go. 2 stars, very close to the sun. There's a solar eclipse, that's why it's black. Okay? The moon is between us and the sun. 6 months later, when the sun was not between the Earth and the stars, then Eddington photographed the stars again. And this time, without the sun bending space-time, the same stars appeared here and here, hopefully. There we go. Okay, so you see the sun has been removed because this was 6 months later, the same patch of the sky. So it's as if the stars had moved a ridiculous amount of distance from where the blue circles are here to where the red circles are in 6 months. These stars are really far away, so it looks like a small distance on the screen, but because it's so far away, it's a tremendous lateral distance. Okay? It's impossible that stars would have had to move faster than the speed of light. Like, stars don't do that. Okay? Moreover, the angular deflection that Eddington found matched exactly with Einstein's prediction. So it must be that starlight is being bent during the first observation, but not during the second observation. Ta-da, Einstein wins. Okay? So a little anecdote here, by the way, that's sort of interesting with the history of physics. When Eddington set up this whole thing in 1919, there was an eclipse in 1919. This was during, he set it up in 1918. This was during the First World War. And he was a pacifist. He was against war. He didn't want to go fight. And so he proposed to the Royal Academy to go and measure this effect that was being predicted by a German scientist. And the English were not too keen on doing that in the middle of the First War, but he convinced them anyways, and he set out to measure this eclipse. Unfortunately, the eclipse, you know how like eclipses work, they don't like make a shadow everywhere on Earth. There's a path for the eclipse. Maybe you're familiar from the Great American Eclipse that happened a few years ago. And so this eclipse in particular was going to go through the equator of Earth, roughly speaking. Okay? So Eddington had to go somewhere outside of Britain to be able to measure this. And so he decided, okay, we're going to go to the Principe Islands off the coast of Africa. But, you know, as a good scientist, he thought, well, you know, I'm going to send 2 ships, one to Principe and one to somewhere else, just in case the ship, this is a ship, like a boat with sails, just in case that thing sunk, because those things could happen in the early 1900s, right? And so he sent another one to Brazil, to Sobral, okay? Now, the 2 expeditions went where they needed to go. Eddington went with the African expedition, and his co-PIs went to the Brazilian expedition. Now, if there's one thing you know about Brazil, is what? It's very hot. It's very hot, okay? And like, it doesn't matter if it's the summer or the winter, it's on the equator, so it's always very hot. And what happens to telescopes when it's very hot? The optics can deform, okay? And if the optics deform, then the focal point changes. And that ruins any photograph you try to take. And that's exactly what happened in Brazil. It was a beautiful sunny day, entirely too sunny. It was hot, and the pictures that were taken out of the Brazilian expedition didn't work. So you're like, okay, well, no problem, just like use the ones from Africa. But the ones from Africa had a little bit a different problem. It wasn't that hot in Africa, in Principe, because it was rainy and cloudy. And another problem with taking a picture of an eclipse is that you can't do that if it's cloudy, right? But the story is, the legend is that during the eclipse, it was cloudy. It had stopped raining earlier in the morning, and it was cloudy. But you know, the eclipse began, and it was still cloudy. But then the clouds parted, and he took like 8 photographs. And then the clouds closed the sky again. And those 8 photographs were enough to make those observations. That's not the actual photographic plates, but it's close to that. And there's some debate as to whether he had enough statistics to make the claims that he made. People repeated this later on. Actually, during the Great American Eclipse, an amateur astronomer just set up a regular commercial camera to repeat Eddington's experiment. And he not only repeated it, he improved over the sensitivity of Eddington's with just regular, like a laptop and like a camera by a factor of 3 or 4. It was like pretty awesome. Like, we can all do this if we want to. All right. It's a bit of a detour, but I think it's interesting. So, of course, the New York Times announced Einstein as the new Einstein, I guess. Or the first Einstein, first genius of the 1900s, and it was a very complicated theory, and it overthrew the whole edifice of physics in some sense. Forces maybe needed to go, and we needed to understand things in terms of space-time. And of course, that's not the only thing Einstein did. I am talking about the theory of general relativity, which he came up with in 1915. So this theory came after all these other incredible predictions that he made 10 years before, okay? So he predicted the photoelectric effect. So the reason that, you know, we have solar cells and solar panels, those physics principles come from him. He predicted Brownian motion, which led to innovations in quantum physics and in biomolecular physics. And of course, he predicted special relativity, which led to the nuclear age. But what I'm going to talk about here, this entire thing, is not about those. Those are like simple ideas, okay? They're groundbreaking. If any one of us could get one of those ideas, we would be set, right? We would be done. Each of those should be a Nobel Prize. He got a Nobel Prize for only one of them, but he struggled for 10 more years to come up with this general theory of relativity, which is what this talk is about. Yeah? Oh, there's a lot of, yes, yes. What? Yes, there were many, many, many predictions he made, especially in his later years. So the theory of general relativity leads to the notion of black holes, neutron stars. It gives birth to the entire field of cosmology, and it leads to the predictions of gravitational waves. Each of those topics could be a separate lecture that I could give. I don't have time for that, so I'm just going to touch on black holes and on gravitational waves because I think they're particularly interesting, okay? So let's talk about black holes. What is a black hole? So take the sun, okay? Earth drawn to scale this time, okay? And let's take the sun and let's compress it to a ball roughly the size of the UIUC campus. Okay? If you do that, if you put so much matter inside of such a tiny ball, the gravity is so strong that not even light emitted at the surface of the star would be able to escape the black hole. As we discussed earlier, light bends due to the curvature of space-time. If you put so much matter in such a small space, the curvature of space-time is insane, and it's so curved in all directions that light tries to get out, but it just bends back and comes back to the center. Okay? So here's my representation of that. Put a flashlight, throw some light, it comes by again. Okay? The boundary, the imaginary boundary that separates the light that can escape from the light that can't escape is called the event horizon of that black hole. And that was a crazy prediction. That was a prediction that was made like not 6 months after Einstein presents his paper to the Prussian Academy, his paper on general relativity. And this soldier called Karl Schwarzschild, who was a German soldier in the First War in the trenches, finds one of the first solutions to Einstein's theory. It's this solution. It's the Schwarzschild solution. It's the solution that describes and predicts the existence of black holes. Nobody knew that these things were black holes at the time. They just were mathematical solutions that were very strange. Yes?
Where did the original idea or concept of a black hole come from for Einstein?
Right. So that's a great question. So nobody predicted this. Okay? Einstein came up with a theory of general relativity, and then other people, physicists, started like playing with this idea and finding what other predictions the theory made. Okay? This is not one of Einstein's predictions. It's a prediction of Einstein's theory made by other people. One of these other people is Schwarzschild. And it's not like he predicted that these things happen in nature. What he found was a mathematical result. He said, I have these equations. If I solve them in some way, I get this solution. And then it took about 50 years for people to understand what that solution meant. What is that? Is that a star? Is that something else? That doesn't look like the black hole thing that I described. Doesn't look like anything else we know of in nature. And so people naturally started asking, are those solutions real? I mean, sure, it's a solution to the theory, but not all solutions to the theory happened necessarily, right? You know, in Newtonian gravity, if I grab a pencil and I throw it up in the sky, there is some initial conditions that if I use those initial conditions, the pencil or the pen will land exactly vertically and just stay there forever, right? Will that happen? Well, most probably not, right? So the same thing here. Do you have the initial conditions to form these things or not? What do they mean, et cetera, et cetera? That's why it's important to go and check, to make a prediction like, oh, these objects might exist in nature. These are the observational consequences. Let's go look for them. So some of the first, there were many observational, observations that sort of began to confirm the existence of black holes. I think the first ones were in the 1960s when, during the Cold War, and the US had a bunch of satellites out there searching for radiation from other parts of the world. You know what I mean? And the scientists, a group of scientists, astronomers actually convinced the US government to maybe point those detectors out toward the center of the Milky Way. And they found a source of radiation, of very intense radiation that they couldn't explain. And that was the first evidence that I know of for the existence of a black hole. People postulated that this thing that was emitting that radiation, I mean, the black hole can't emit the radiation, but stuff that's falling into the black hole can. And the energies were so high that the only thing that could be producing so much gravity to produce so much acceleration, to produce so much light from things falling in would be a black hole. Fast forward now 40 years, and several telescopes have now imaged the stars that move around the center of our Milky Way, where that source of radiation is. And of course, if they point their telescopes at the center of gravity, they don't see anything because no light escapes from a black hole. But they see all of these other stars moving in these elliptical orbits. And they can track those stars, and they can measure those orbits. And then they can ask, well, if those orbits are real, somebody has to be curving, something has to be curving the geometry of space-time. What's the mass of that object? What are the properties of those objects? You can calculate that using Einstein's theory. And you do that, and you discover that this object is incredibly massive, 4 million times more massive than our sun, and it can't have a radial extent that is larger than roughly the sun. So you put 1 million times the mass of the sun inside of the sun. Okay, if you did that with regular matter, you would see a lot of light in Newtonian gravity. If you do that in Einsteinian gravity, you form a black hole. Okay? So this is the first, I would say, indirect evidence, because you get information about this object from the motion of other objects. Fast forward 20 more years, and people started realizing that maybe there was gas that was falling into this black hole. And that gas was the gas that was emitting this light that was observed in the 60s. So maybe, just maybe, if you put enough telescopes around the Earth, and they're big enough, and you then work collaboratively across many different countries. You put a telescope in Chile, you put a telescope in Hawaii, another one in Virginia, you throw some telescopes in Europe, and maybe one in Australia for good measure. And then you combine all of that data, maybe you can image the accretion disk, the gas, as it's falling into the black hole. Okay? That is what the Einstein telescope did. So that's the black hole. This is light from all directions that is bending because of that black hole. That's a simulation of what the gas would look like. There's nothing in the middle because that's where the black hole is. And that's the data. Okay? That's a picture of a black hole. Of course, if I just showed you the black hole alone, I would just be showing you a screen of black, and then you would laugh. That's not a photo of a black hole. What I'm showing you is the things that are around the black hole. Okay? Yes?
What kind of telescope can see that?
Great question. So these are giant dishes that detect radio emission. So radio is, when we say radio, what we mean is light of a particular wavelength, of a particular frequency. It's the same frequency that we use for radio communications. Yes, sir.
First realized that all these stars were going around the black hole.
Great question. So
What year is approximately was that first postulated?
right. So the first calculations that suggested that if you have a black hole and there's things moving around them, then these orbits could be very interesting. That was done in the 60s, 60s and 70s by Kip Thorne, who I'm going to discuss later. But nobody knew if there was anything close enough to the black hole at the center of our galaxy so that we could point a telescope and see those stars. Of course, if there's no stars, then you can't see anything going around it, right? And there's no guarantee that there are stars that close to a black hole. And so it was not until the 80s and 90s that people had telescopes with enough resolution to be able to see these stars.
So before that, nobody realized that
Nobody knew if there were stars there or not.
stars were actually going around.
Yeah, it's like you're looking at a point in space that's very, very far away with a really bad camera, and you don't have the resolution to see if there's actually light moving around or not. And it takes a very long time for these orbits to complete, so you have to observe for a very long time. So it required the advancement of optics in general, the creation of something called adaptive optics, where you can sort of adjust dynamically to improve the precision of the camera.
Just to follow up, you have two different black holes and the stars going around them.
Yeah.
What happens to the ones that are right in between the two black holes? Does anybody know? How do they
Great question. So,
jump from one
let's put a pin on that one because I'm gonna talk about binaries in a second. Okay. So I just want to also mention that members of the Event Horizon Telescope are like working in this building. Charles Gammie, for example, is a numerical relativity physicist, and he was one of the people that made the predictions that I showed you in the previous slide. I think that's one of his animations. Okay? Many of us work on black holes. That's a pretty cool thing. So what happens if you have a binary? Okay? What happens if you have two black holes? One black hole curves the space-time geometry. Two black holes also curve the space-time geometry. And if they are moving around in a circle, then that curvature won't be static. It'll start changing, okay? And it'll produce ripples in space-time. Just like if you take a little tugboat on a pond and you just move it around, it'll produce ripples on the surface of the pond. Or if you put two of such tugboats going around each other, they will also generate these ripples. That's what should happen, and that is something that Einstein actually predicted. Funny story about that. He predicted that those gravitational waves were not real. Then that paper got rejected. He got really pissed off that somebody rejected one of his papers, famously telling the editor that he sent papers to him for him to publish them, not for him to review them. At that point, he was super famous. But fortunately, it was reviewed. The referee that reviewed that paper was anonymous. He was a famous physicist, I think it was Robertson from England, actually went to Princeton incognito to talk to him and to talk to his postdocs, his assistants, and convinced him in talking that he was wrong. He then revised that paper and resubmitted it with the correct answer, which is that gravitational waves are real, to a journal, and this time it was accepted. Okay? So this idea that you might have, talking to the students, that Einstein was a genius and was never wrong is totally flawed. Okay? Einstein it took him 10 years to get to general relativity because he kept on getting the theory wrong over and over and over again. Okay? And it's not because he was bad at math. He was not bad at math. He was also not a genius at math like Riemann or Poincaré. His genius was in his creativity, in his ability to unify ideas from disparate fields, okay? So, can we detect these gravitational waves? So back in the 70s, I want to say, there was this young professor at MIT. His name was Ray Weiss. And he has a super interesting story where he quit college to pursue a love interest that he had in Chicago. He quit physics at MIT and went to Chicago to pursue that relationship. That didn't work out. And then he tried to come back to MIT, but by then he had already left for too long. And so MIT was like, I don't know. And he convinced some professor in some lab to take him on as an assistant and eventually finished his degree. Almost got the Nobel Prize for a completely different physics idea. And then became a professor at MIT. And when he was there, they decided they would teach a class on general relativity. He was a young professor. He's like, okay, you teach the class. And then he thought, like, what a great idea to create a problem set that asked the grad students to imagine how you would detect gravitational waves. Okay? Nobody had come up with that idea before. And he just asked the grad students to come up with something. And of course, the grad students failed miserably because nobody knew how to do this. And then he realized that this problem was maybe a little bit too hard when he was creating the solution set for that problem, okay? And it was so interesting, the solution, that he published it in an MIT Technical Communication. And that solution is the basis for the method we use today to detect gravitational waves, which is called interferometry. Interferometry has existed forever, since the early 1900s. But interferometry, as I'm going to explain it now for gravitational waves, that was his innovation, okay? So let's imagine that you have two vacuum tubes and you have a laser, not this one, that one, and you have a beam splitter. What the beam splitter does is, well, it splits the laser beam in two perpendicular directions. And let's say that there's mirrors at the end of these tunnels and that light bounces off each of the mirrors, it comes back here, it recombines. Great. We've recombined, we've split the light and we've recombined the light. But if a gravitational wave goes through, then space-time stretches, right? Just like I showed you earlier, there's ripples in space-time. So that causes the light that used to recombine perfectly to recombine in a way that such that there's destructive interference, constructive interference, destructive interference, constructive interference. When there's destructive interference, the two light beams that combine, they cancel each other. When there's constructive interference, the two light beams that combine, they enhance each other. So if you're here detecting something with a voltmeter, you see a lot of light, very little light. A lot of light, very little light. Even though nothing is moving the mirrors. Okay? So by tracking the motion of that interference pattern, you can learn about what's producing the stretching of gravitational waves. That's what he predicted in the 70s. Took about 30 years. Well, it took about 20 years to convince the government that this was a worthwhile experiment to do, in part because it required inventing new lasers, new vacuum chambers, new mirrors, new suspensions. Like none of this technology existed. It needed to be created, okay? Of course, then those patents led to other innovations. That's how physics works. But of course, it also led to the creation of this interferometer. So here are movies of the instruments, one in Louisiana, Baton Rouge, near Baton Rouge, and one in Washington State, near the nuclear reserve. These are the tubes that I was telling you before. They're of course not exposed to air. They are enclosed. They're like roughly this big, okay, around, and they're 4 kilometers. So that's 3 miles, okay, in each direction. And that's one of the end stations. That's where the mirrors are. Yeah. And then LIGO turned on roughly when I began my grad studies in 2008. Is that right? Where's my wife? 2003. 2003. Okay, thank you. And you know, we started like trying to detect these gravitational waves. I was involved. I had to go to the nuclear reserve and see if we'd detect things. And then there was a huge explosion in the nuclear reserve that knocked the instrument offline, and we were all very worried because it happened at 2 a.m. in the morning. Turned out it was a controlled explosion. Funny things happen at that nuclear reserve in Washington. Nothing serious. They had planned it. They just forgot to tell us about it. And we did that for like 5, 6 years, and we observed absolutely nothing. It was delightful to be a grad student collecting noise for 6 years, okay? Then I became a postdoc, and then eventually became a professor at Montana State. And when I was a professor, when I was not going, was too old to be doing the graveyard shift in Washington State, so I got to stay in my comfy office doing my calculations and whatnot. And then in 2015, something happened. The detectors turned on again with that enhanced sensitivity. They had made the instruments more accurate, okay? More accurate than they had ever made them until that point. And they observed gravitational waves from 2 black holes going around each other, roughly 30 times the mass of the sun each, colliding at roughly half the speed of light, about 4 billion light years away. Is that right? 1 billion light years away. Very, very far away from us. They collided, they produced this burst of gravitational waves. Those waves travel at the speed of light. They interact very weakly with anything between us and the source. So they go right through, they hit Earth, totally not to scale, but they deform space and time, okay? Unfortunately, we had these super accurate detectors. That's Hanford in Washington. And the waves were going through, this instrument was on, and ta-da, you could see the interference pattern. For the first time, the prediction that Einstein had gotten wrong and then right was confirmed. Okay? So what I'm going to do now is I'm going to show you the frequency of these gravitational waves as a function of time, and I'm going to show you the power in the signal. There's 2 of them because there's one detector in Washington and one detector in Livingston. And what I'm going to do is I'm going to convert the waves into a sound file. Because interestingly enough, the frequencies of these waves are within our hearing range. So I can just play them onto a speaker. Okay? Those speakers over there. So here we go. Okay. So I obviously looped that. We only heard that once, the loop, okay? And the reason that you see a lower tone one and a higher tone one is because I just transposed the octave so we could hear it better, because otherwise it's too low. The thing that you see here in time, this is the data itself of the gravitational wave. This is what the instruments detected. What you see here is the power as a function of frequency. And that was a Nobel Prize, okay, in 2017. Shortly after, fast forward 2 years later, they detect this, 2 neutron stars, which I didn't have time to talk about, but they are also super interesting objects. They are as massive as our sun, but not as dense as a black hole, okay? They observed 2 of these things colliding with each other. This observation then led to the conclusion that most of the gold that we have access to today, if you have anything made out of gold with you right now, chances are that was made in the collision of 2 neutron stars. So I know that most of you know from Carl Sagan. If you don't know who Carl Sagan is, young people, you should go Google it. That we are, what did he say, like made of stardust, okay? Because like, oh, you know, stars are born in supernovae, in these giant explosions, and that's, you know, how we get all the elements. That's almost true. Not all of the elements, not gold. Gold doesn't come from exploding stars. Gold comes from colliding neutron stars, okay? And a bunch of other heavier elements too. So let me do the same thing and show you the frequency as a function of time, the power that was detected at the LIGO instrument. I'm going to also sonify that. And interestingly, you know, I told you black holes don't emit light, right? So when 2 black holes collide, you can't see that in telescopes. When 2 neutron stars collide, those things do emit light, okay? So in principle, you can see the light from the collision of 2 neutron stars. And that's exactly what happened with a NASA telescope called Fermi, which was in orbit. So I'm going to show you the Fermi data here and the gravitational wave data here. You ready? Here we go. Okay, gamma rays don't make a sound, okay? Light doesn't make a sound. I just added, well, actually Neil Cornish added that sound here just for comic effect. But what you know is that there's an excess of photons over the background. It suggests we've detected photons, light. We've detected light of a certain energy shortly after the merger of 2 neutron stars. That's because what we see is not the light from the stars themselves. What we see is the light they emit after they collide. But they collide at this point. It takes the light a little bit of time to actually form jets that can actually escape that very dense environment. Exactly 1.7 seconds is how long it takes for the jets to form, okay? Yeah, so this event happened 2 years later. This event also, by the way, confirmed another prediction of Einstein's, which was the speed at which gravity waves travel. How do we know that? Okay? We know that because we know when we detected this gravitational wave, this light, and we know when this light could have been emitted. It could have been emitted at most at this time, or maybe a little bit later. There's some band of uncertainty here. We moreover know where this source was in the sky and how far away it was. How do we know that? Because we have a bunch of other observations from a bunch of other telescopes observing a bunch of other stars in the same galaxy where this thing is at. So we know which galaxy this thing came from. Okay? So we know the galaxy, we know how far away the galaxy is, and we know how long it took for the light to get to us. and we know the speed of light, so we can calculate how long or how fast gravity moves at. Einstein predicts that gravity moves at the speed of light, just like light. This confirms that prediction to 1 part in 10 to the 15. That means the speed of gravity, according to experiment, is the same as the speed of light to 0.00000000000 14 times 1. Okay, that's the error. Okay. So, of course, there are many more gravitational waves that you can detect, and you can put all of these sounds that I showed you before together, and students have done that to create this little piece of music. These are all sounds from merging black holes superposed with like actual music. Okay? And of course, we haven't just detected those 2 events. We've detected at least 90 of them. Actually, more than that. That was 90 events as of like 6 months ago. I don't quite know what the tally is at now. Kristen, do you know? Caroline? No. Okay. So mostly, we've observed black holes. We've observed 3 neutron star events. Some of those were a neutron star and a black hole. Detected the gravitational waves, the properties of the systems beautifully. And so we have once more confirmed Einstein's prediction of gravitational waves. Okay? Similarly, we've also confirmed Einstein's predictions, the predictions of Einstein's theory. That one he didn't make. Other people predicted neutron stars. But we've observed those neutron stars. We have observed how those neutron stars move around each other. And that led to another Nobel Prize in the 1980s by Hulse and Taylor, which is also related to relativity. And of course, we observed the microwave background of light from the very early universe, the cosmic microwave background, the CMB, which is a prediction of cosmology, which arises from general relativity. So, is Einstein still right? That is the name of the book, by the way, which I didn't put a link to, but you can ask me later. And the answer is yes, so far. Okay? Why do I say so far? Because Einstein's theory is not complete. We know it's not complete. We knew it was not complete in the 1930s. We knew it was not complete in the 1950s, in the 70s, in the 90s. We still know it's wrong today. Why do we know it's wrong? Because it does not play nice with quantum mechanics. And we definitely know quantum mechanics is right. You know, I love my cell phone, maybe not as much as my daughter, but I love my cell phone. And that works because of quantum mechanics. But quantum mechanics is a completely different theory, and it's completely incompatible with Einstein's theory of general relativity. So what do you do when you are trying to predict phenomena where both quantum mechanics and relativity should be important? We don't know. Okay? We don't have theories for that are complete, okay, where we can make a precise prediction. We also don't have observations that can probe that regime to get guidance yet. Our technology is not advanced enough, and nobody has come up with a good idea to do that. But that's the frontier. So what are people trying to do? Well, one of the things people are trying to do is trying to detect more of these gravitational waves, because maybe in this gravitational wave motion, if we look at other sources that we have not detected yet, maybe there's a hint, a signature, something to tell us how to correct Einstein's theory to make it compatible with quantum mechanics. One of the things we have not observed is a small black hole going around in orbit around a supermassive black hole. So what happens if you have a black hole the size with the mass of the sun, okay, going around a black hole like the one at the center of our Milky Way? Well, the orbits look way more complicated. Okay, that's a small object. This is the big object. I'm going to show you a movie. The waves are also different, and you can hear the difference. It sounds like a motorcycle. So every time the small object goes around this big black hole, it's acting like a tracer of the geometry. It's like making a map Okay, if you want to make a map of the Americas back in the 1500s or 1600s, what would you do? You would just send a boat to go and trace the shape of the continent. Well, same thing. If we want to know what space-time is like around this supermassive black hole, we got to send something that can probe its boundary. Okay? We can't send anything. It's not like we're going to send a black hole. It just turns out these small black holes are predicted to exist around supermassive black holes. The problem is this signal, the gravitational waves, are too low a frequency for us to detect on Earth. See, something I didn't tell you is that we cannot detect all of the gravitational waves. We can only, on Earth, we can only detect the gravitational waves on Earth that the instrument that we've built allows us to detect. And it turns out there is a wall of sensitivity at 10 hertz. Anything that happens below 10 hertz, we are just deaf to. We cannot hear it. Why? Because Earth is in constant seismic motion. And that seismic motion shakes the mirrors. And that shaking of the mirrors introduces noise. And that's noise that we cannot separate, that we cannot model. We don't understand how the seismic plates move to enough precision to model that out. So we're deaf below 10 hertz. So what do we need to do to listen to these gravitational waves? We got to go to space. Okay? Because there's no seismic motion in space. So for the last 30 years and counting, maybe 40 years now, people have been working on what kind of detector could we place on Earth. And they come up with this design where you have 3 satellites in orbit around the sun, not around the Earth. They are each on an orbit that looks like Earth's orbit. Show that again. And it's trailing Earth with this triangle arrangement rotating around. There's light, there's laser light that's been shot from one spacecraft to another spacecraft, and then from that one to this one, and so on and so forth. And by keeping track of how long that light takes to get from one satellite to another satellite, and then to another satellite, and so on, we can measure with insane precision the separation between the satellites in that triangle. So if a gravitational wave goes through, that triangle is going to deform. Again, it's going to produce an interference pattern, and that we should be able to measure. That's a mission that NASA is involved in, that ESA, the European NASA, is involved in, and that is scheduled to launch in 2034, before I retire. Yay. And so we're all very excited to see what this mission and many others will observe in the future. Can we turn the lights off, Jan? So to conclude, I want to show you a little movie to get you all excited about the future of gravitational waves. Perfect. Thank you.
Wonderful. So we have time for questions from the audience. So I can moderate here the questions. Let's take you in the back here, raising your hand.
Yes, hi.
Yes, great lecture.
Thank you.
My question was about gravitational waves and how much energy they carry. And when we measure the gravitational waves, is it a decreased version that you're getting, or does the energy dissipate from? Because you mentioned it's like a couple billion light years away, right? But it start with more energy by the time it gets to us, it's a lot weaker. And how does that energy transfer work?
Great question. So, yes, one of the big questions about whether gravitational waves were real or not, I mean, the debate continued after Einstein said they're real. It continued through the 50s and the 60s. And one of the big questions was, do gravitational waves carry energy or not? It's a complicated question because in general relativity, you can always boost yourself to a frame where space-time at that point and very close to that point looks completely flat. Of course, outside of that point, space-time can be curved. But at that point, it's flat, so the energy there is zero for gravitational waves. So how can it be, if a gravitational wave is real, how can you just go to a frame and have zero energy? And so Feynman came up with a solution. He was not a huge fan of gravitational wave physicists because, of course, they had no data, so there was no clear indication whether this whole Einstein thing was correct for that particular solution. But Feynman said, look, it's very simple. If I just take two balls and I touch a spring around them, and I have a gravitational wave going through, then those balls will start moving. And that's going to stretch and compress the spring. That's going to heat up the spring. That heating up of the spring is energy that got transferred from the balls that are moving, which got transferred from the gravitational waves. Therefore, this is real. I don't know what you're all debating about. Just go and build a machine to measure it. Which actually then prompted another scientist. What's the name of the person that almost claimed the detection of gravitational waves? All right. There was a false detection of gravitational waves in the 80s. That's the person that set up to measure this. Anyway, doesn't really matter. The point is, gravitational waves definitely carry energy. How much energy do they carry? Well, these events, I totally played a little bit of a trick on you. I slowed down the motion of those black holes so that you could see it. But when two black holes are colliding like that, the last stages last like less than 0.1 seconds. So if I play it at real time, you can't see it. It's just too fast. Okay? And during that 1 second of observation, those gravitational waves emitted contain more energy than the output of all of the stars in the universe put together. Okay? But it's energy you cannot see. It's not energy that appears in light in the electromagnetic spectrum in photons. It's energy that is in gravity. Of course, it's a very short, we call it a transient event. There was nothing before it, then the things collide, there's nothing after it. It's actually not quite entirely true. Before it, the gravitational waves are there, but they're weaker, and so they're not carrying a lot of energy. Most of the energy comes from the collision itself. Right? And yes, you are right. When the gravitational waves get produced, they have this energy and they have this amplitude, okay? And then they travel. And as they travel, the amplitude decreases. It decreases inversely with distance. And so by the time they get to Earth, they're way weaker than when they were emitted. So weak that we need to build these ridiculous machines to be able to sense the motion of the mirrors, which is on the order of 1/1000th the size of a proton. That's how much the mirrors are moving. That's why I said when the Earth turns into jello, it's really out of scale. It's like really out of scale. Okay? And so that energy is still there, but it's dissipating. So the energy on a sphere, right, is essentially remaining constant as you go to other spheres.
So based on the energy, can you predict the distance of the source?
Yes, absolutely. So from the amplitude, from gravitational waves, you can get the distance to the source. plus minus 50% because there's correlations with other parameters. But that's exactly how we do this kind of business, right? So you detect these gravitational waves, then somebody has to construct a model for what the waves look like, and then you have to compare that model to the data. And the model has parameters in it, the distance, the masses, the spins of the black holes or the neutron stars, all sorts of other things. And so what you need to do is you need to take that model and you have to compare it to the data for all the possible combination of parameters of the model. And because there's at least 15 parameters in the model, depending on how complicated the binary is, there's billions of combinations that you can try. And you cannot do it on your laptop. Okay? You cannot do it on 2 laptops. You have to do this comparison in clusters of supercomputers. So here we use the computers at the National Center for Supercomputing Applications, NCSA, which is that way. Okay? And so my group, 2 members here, raise your hands. Okay? So this is 1/10 of my group. And what we do, one of the things we do, is we construct these models first, and then we compare the models to the data by varying the parameters with very sophisticated algorithms, which, by the way, are similar to the algorithms that the National Spy Agency, what's that one called? The NSA.
NSA.
The National Security Agency uses for other purposes. Okay. Yes?
Oh, let's see. Yep.
So Einstein said there's no such thing as gravity. This curvature is space-time. So we got quantum theory that said, we got a graviton. How does that fit in the picture?
Great. So, yes. So Einstein was one of the first people to postulate that light maybe was not a wave, but if it was a particle, a photon, then maybe that photon could carry energy that could be then recovered through a combination of wires, or something we call the photoelectric effect. So conversion of a photon into electricity. If you have many photons, then light doesn't act as a particle anymore. It acts as a wave. The same is predicted from Einstein's theory. Einstein's theory, if you just make an analogy with quantum mechanics, predict that gravitational waves exist, and you can imagine these waves as a bunch of gravitons together, collectively moving like a wave, or as individual particles. The problem is that unlike photons, we have no way to harness those graviton or the energy in those gravitons, and that's in part because we don't have a complete theory for what a graviton is. Because now you need to combine quantum mechanics with general relativity. And so it's not clear. So if you take the naive, incredibly advanced physics theories we have today of quantum electrodynamics, combine quantum physics with electrodynamics and so on to understand what a photon is, and you try to lift that and apply it to gravity, then you would predict that there's gravitons and blah, blah, blah. But you get into problems because that theory becomes really bad. It becomes incompatible with nature, with the predictions of nature. So the simple, we take what we know and we apply it to gravity, just doesn't work. And so we don't know. We don't know what a graviton is, whether gravitons exist or not. Sorry. Correct. So it is possible that something like a graviton exists, but not exactly the graviton that you would predict from quantum electrodynamics. But we don't know.
Question in front.
Is this a single wave particle duality?
Yes.
Deltas?
Yes, that's exactly right. The same kind of thing.
Question in the back here on the left.
I presume there are also gravity waves within the solar system. How do their strength or visibility compare?
Great question.
Would they ever be visible to us?
Yeah, that's a great question. So everything that's massive and accelerate produces gravitational waves. Everything. I'm generating gravitational waves right now. Moving my arms up and down, accelerating them, that produces a gravitational wave. The problem is that the strength of the gravitational wave is proportional to the mass that's being accelerated. And the mass of my arms is nothing compared to the mass of a black hole. And the mass of the sun is comparable to the mass of a black hole. But another little trick that I didn't mention is that the strength of the gravitational wave doesn't just scale with the mass, it scales with the density. So how much mass can you generate in a small sort of volume? And the sun has a ton of mass, but it's all spread out over like 1 million kilometers or so. And so, yes, Earth, as it moves around the sun, generates gravitational waves. Mercury does it too. All of the planets do it. We do it constantly. But the amplitude of those gravitational waves is like 20 orders of magnitude below what we can possibly detect. And we are already at what some people call the quantum limit of interferometry. So we are detecting things so precisely, the motion of these mirrors, the interference so precisely, we are beginning to collide with the laws of quantum mechanics, with the uncertainty principle. The uncertainty principle tells you you cannot measure position and velocity infinitely accurately. So if I want to measure the position of the mirrors with ever increasing precision, then the velocity of the mirrors becomes uncontrolled. And so we have to play games. And new technology has been invented to circumvent that photon shot noise that we call, and that was developed by people at MIT. And it's being deployed right now in the current observing run of LIGO for the first time.
More questions? Here, in the back here.
Have there been any collisions that have been observed in our local star group?
No, to my knowledge, all the gravitational waves we have observed have been extragalactic.
Go ahead.
Yeah, I guess the E equals mc squared. Can mass turn into gravitational energy? When those fly?
Yes, absolutely. So one of the predictions of Einstein's theory is, as you said, that energy and mass are in some sense interchangeable. You can convert energy to mass and mass into energy. When two black holes collide, right, the black holes have a certain mass. Therefore, they have a certain energy, mc squared of this black hole, mc squared of this black hole. Then they collide, and they emit a bunch of gravitational waves, which carry energy. That energy gotta come from somewhere. Okay? Part of it comes from the energy of the orbit, the kinetic energy, if you want, of the objects as they're colliding. But part of it comes from the rest mass energy of the black holes. So after they collide, if imagine I have a black hole of 30 solar masses, Jan, and I'm another black hole of 30 solar masses. We come together. Good friends we are, okay? We're now one object. We are not 60 solar masses because some of our energy went away. We lose roughly 5% of our mass to gravitational energy. Great question. And that's been measured.
Time maybe for one or two more questions. Okay, go ahead.
So usually the story is Einstein created his theories, and then people find solutions to these things, and then we create instruments to do that. So one example of a solution is like a word bracket, all these sort of things, or I mean, not a word bracket, wormhole. So is the and I'm sure there are many more of this solution that we haven't really tested out yet. So if that's the case, it should focus, like, should a big part of the focus of the physics community should be just focusing on the engineering of this, testing or like sensitivity tools to make progress in physics, or what do you make of that?
Yeah, so I'm not entirely sure I understand the question, but let me attempt an answer, and then you can tell me if I hit the spot. So the first thing I would like to say is that Einstein didn't come up with his theory by himself. Okay? No one comes up with a theory like Einstein by himself. That's a lie that we unfortunately have told many, many students, okay? Everyone is the product of their time and of their environment, and they feed from the research that's happening around them. Einstein had a guy called Riemann, and a guy called Minkowski, and a guy called Gauss, and a guy called Marcel Grossman, who's a good old friend of his, contemporaneous actually to Einstein. He had friends like Mach and others. Together, his wife. Thank you. Right. Tons of physicists, all in Europe, because there was a communication situation there where you could just like not really reach out. But you know, it is together that they create an environment where somebody can have an idea where like they say, okay, well maybe this thing is right, and then everyone else just jumps on that boat to try to prove or disprove that theory. Okay, and so if you ask me where should the effort be spent in physics, which I think is your question, I think the best approach, and this is now a personal view, I'm putting my lecture hat off, is that we should diversify our efforts. We shouldn't put all of our eggs into one basket and say, this is the right theory, be it Einstein or something else, and just work on that. If we all just spent time finding solutions to the Einstein equations, many of which may never be realized in nature, we would be missing out in understanding ways in which we can detect those predictions. That requires technology that we also need to push. Okay? If we concentrate only on a particular solution because we just want that one, we miss out on all of the other solutions that may be present. So I think what we should be doing is some people should be looking at certain solutions, some people should be looking at other solutions. We should all have in mind that these solutions ought to be compared to data. Other people should be working on data because data is so large nowadays. We're collecting so much data that we require special computational algorithms to actually analyze it. Okay, how can we use, for example, artificial intelligence technology to speed up our computational codes to analyze data? And other people need to be working on the experiments itself. Like, how do we build the machines that will allow us to collect that data so we can then compare to the models and to the predictions? All of these things are connected. We like to silo ourselves and like, oh, the theory is over here, and the experimentalist is over here, and the data analyst, well, that one's not even in physics, that one is in the statistical department or in the computer science department. Although nowadays, most of those people are also in physics. But not always do we talk to each other. And not always do we actually talk to people in other fields. Because it turns out gravity, like everything I just described here, doesn't live in isolation from all of the other fields of physics. If you want to understand neutron stars, you've got to understand nuclear physics, you've got to understand high energy physics. If you want to use gravitational waves to understand cosmology, probably you should be talking to cosmologists. Or dark matter, you should probably be talking to particle physicists. If you want to understand how to improve the detectors, you probably should be talking to people that work in optics and condensed matter. Are there new materials that we can use to improve our detectors? And so on and so forth. So everything is interconnected. And that's where we, I think, should be spending our energy on, or what we should be doing.
I think that's a nice place to end, actually. It's kind of a forward-thinking statement. So let's thank Nico again for really stimulating discussion. So our next Saturday Physics for Everyone lecture is going to be on, I think, 2 weeks from now. So I think it's December 2nd. Great to see everyone here again, and I hope to see you for our last lecture of the semester. Thanks, everyone.
Thank you.